Hello and welcome back, and in this video we will cover something related to deep NLP. So as the title suggests right here, we are going to cover sentence classification using transfer learning with HuggingFace BERT and weights and biases. But as to most of you, those who have been following the news or the trends related to NLP in the recent days or months or years, you must have heard about HuggingFace as well as BERT. So these are the two of the most common names in the field of deep NLP in the recent days, in the modern days. So what is BERT? BERT, which stands for bidirectional encoder representations from transformers. So this is the abbreviation for this. BERT is just an abbreviation of a model. It's a transformer based model. So if you don't understand what a transformer is, it's a deep learning based model. It has been known to perform better than the classic RNNs, LSTMs, GRUs and stuff. So it was released in late 2018 by Google researchers. And so what happened was, around this time, at the end of year 2018, they released Transformer and this BERT model. It took the NLP world by storm. So it beat all the previous model. It did beat all the previous models in terms of all of the classical NLP problems. But the surprising part was that it also beat some of the human level performance. And another surprising thing was that the transfer learning that BERT made possible was never possible before. So you could train your own production level state-of-the-art NLP, deep NLP model on a single GPU or maybe on a Colab, which was not possible with the RNN based models that required a lot of training time as well as powerful systems. So that is why BERT has been used. That is why BERT and its derivatives have been used and are being used by most of the deep NLP tasks these days. Now, let us have a quick look about the advantages of the BERT model. So this approach is better than training a deep model like GRU or LSTMs, as we talked about from scratch, as the pre-trained BERT weight model already encode a lot of information about our language. As a result, it takes much less time to train our fine-tuned model. We'll train BERT on our model with hyperparameter sweeps to find the best combination within an hour on Colab, while training a single deep RNN model from scratch would take more than hundreds of hours on GPUs. So previous models, RNN-based models, were trained for weeks on end by researchers in big corporations on their large virtual machines. But we can train our own language model based on BERT, and we can also train multiple BERT models and choose the best one within an hour. So this is the power that it provides. So the second point is, as we are essentially performing transfer learning, we need significantly less data to build an accurate system compared to millions of data points required to train a model from scratch. We can accomplish the same tasks with only a few thousand data points, as you will see in the code section. We will build our own language model and using only thousands of data points, not millions, because we can already use the model BERT based trained model that is available online for free. This is a pictorial representation of BERT. So first of all, you can see the input right here on the first line. So let's just say my dog is cute, he likes to play. All of these, there are special characters. The first character represents the kind of task that we are trying to do. So BERT enables a lot of tasks. So the kind of task that we are trying to perform on this BERT this BERT model has to be specified by a separate character. So that a separate string, that is CLS classification. And so there is now SEP is separator, so it denotes where the sentences get separated. Now the thing is, there is a special way or multiple ways in which BERT is trained as a language model. So one of the ways the base model is trained is by masking few of the words at random. So masking basically means that you have to cover up or basically delete a word in between, and then you have to train a model to predict that word. So in this way, it recognizes how a language should look like. So this picture just demonstrates an example input while training this BERT model. So what happens is they add special characters such as CLS in the beginning and separators of that, and the mask on top of dog and likes represent the word that were masked. Okay, so in the next layer, token embeddings, these are all transformers, right? So in the next layer, you can see the words that were masked are not written. It is just replaced by a special character called mask. So basically this happens, and there are multiple transformer layers, and they finally try to classify this. So in this way, the BERT model is trained. Now, there are a lot of details about how transformers works, about how there are encoders and decoder transformers, but we will not cover those things in this video, because this is more of an implementation video, right? Because you have to cover Hugging Face and etc. So let's move on to the real world problems that BERT has solved since its inception. Okay, so Google said that BERT helps understand the nuances and contexts of words in searches and better matches those queries with relevant results. So it has also been used for feature snippets, and here's the example. So as you can see, if someone searched for 2019 Brazil traveler to US needs a visa. So basically this picture compares before and after queries, right? So before BERT was used to understand the context of the question. The result would be something like which is shown on the left. US citizen can travel to Brazil without the red tape of a visa. I don't know what that is, but anyway. But after BERT, it understands the context, and it displays a very different result. That is US and tourism and visitor, US embassy and consultancies in Brazil. So it gives a completely different result. Now I think this picture tries to demonstrate that the second result is more accurate, but I don't know what he meant in the first place. So anyway, but here's the thing: the model that we can train these days on a single GPU within an hour or less is actually being used as a field of NLP in some form, in a way that we can also researching it. So try to build our own. So these technologies such as BERT and Hugging Face lab. Now let's move on to Hugging Face. So what is Hugging Face? Hugging Face is basically a library that has open sourced all of these implementations of different transformer based models. So now they have changed the name of the library to basically transformers, but the company is known as Hugging Face, and they have all of these implementations in both TensorFlow and PyTorch. They have these implementations of all of the state-of-the-art transformer models, including BERT derivatives, and if you have heard about all of these things such as RoBERT or DistilBERT and all of that. So they have the implementations, pre-trained models, and training scripts and stuff. So you can easily use these models for production using Hugging Face library. So it's a really well-written tool, and it is really easy to install and get started with it. So, and by the way, this tutorial is based on Chris McCormick's tutorial, which is a really well-written tutorial. So I have edited a few of the things, and I have added parameter sweep so that we can train multiple models automatically and select the best ones and visualize them. So now what we will do is we will train our own BERT model from scratch, and we'll also train multiple of them. What we'll do is we'll train multiple BERT models with different hyperparameters such as batch size, number of epochs, learning rate, and then we'll choose the best one based on its validation accuracy. So the model which has the best validation accuracy. So here are all the runs that I've already trained it once, so I'll just walk you through it. But here are all the different combination of hyperparameters, and the best one is in that combination is somewhere this, which is 16 batch size and 3 epochs with learning rate of somewhere 3e-5. So here's the thing. Here is the pictorial representation and comparison of all the runs, and here is all of the runs and the validation accuracy, in form of a graph. So I've gotten all of these graphs, all of these visualizations automatically using weights and biases software, which I'm going to be using, which basically automates the process of model comparison and visualization. So here is the training loss of first 20 runs. So as you can see, it's easy to compare which model performs the best. Here is the validation accuracy, here is the average training loss, average validation loss, and all of these things. So first of all, as I've already walked you through what BERT is, let's just install HuggingFace library. So to install HuggingFace library, you just need to write this pip install transformers, because most of the transformers are already been implemented in this library. So to train this sentence classifier, we'll use the Cola dataset. So a little bit about that, we'll use the corpus of linguistic acceptability dataset for sentence classification. It is a set of sentences labeled as grammatically correct or incorrect. It was published in May of 2018, and it is one of the tests included in GLUE benchmark. So GLUE is basically a benchmark that that calculates how well a language model performs, or NLP model performs. So in GLUE there are like 9 tasks, and the average score of that tasks is used to calculate the leaderboards. So it is one of the tasks in GLUE benchmark. So here's the code. You just have to install the dataset, which is a zip file, and we'll just extract it. Nothing serious going on here. Okay, so first of all, okay, so we'll just read the CSV file and print the number of sentences that we are going to train on, and we'll print the sample. So as you can see, there are only 8,500 sentences about that, and we'll train a large language model. Well, we're just fine-tuning, but the first advantage of BERT was that we don't require a lot of data, so we can train it only on 8,000 sentences, and it works fine. So this is the format of the data. So first of all, the sentence source, which is not required. Again, label, which is required, that is grammatically correct or incorrect. Okay, so yeah, basically that. So we just need these 2 things. So let's extract the required data. The first is sentences, and the second is label. So now second thing is tokenization. So I guess if you're watching this video, you already know what tokenization is, but I'll quickly walk you through what it is. So first of all, computers don't recognize English words, so we need to encode them into numbers. So what happens is, a tokenizer is trained on a corpus that contains multiple words, probably 50,000 or 100,000 or maybe more. So each word is assigned a number. So tokenizing a sentence means assigning that number to each of the word of the sentence. So for example, this sentence original, our friends won't have to buy this analysis and whatever. So first of all, to tokenize it, we'll first separate each token. So tokenization means the first step is to separate out a sentence into words, and each word will be called a token. So everything is separated, right? And then these tokens are assigned their IDs or their indexes of the word, so that we can represent a word in form of a number. So in that corpus, whichever corpus this tokenizer is trained on, in that corpus the word hour should be at this index, that is 256, and so on. And now we'll use this instead of the original sentence to train anything. So sentences that we're going to classify should be fed into BERT model, but these must be first tokenized using BERT tokenizer. Now we cannot use a tokenizer of our choice because as stated previously, we are performing transfer learning, and the base model is already trained on data that has been tokenized by using BERT tokenizer. So what we'll do is we'll use BERT tokenizer for this task. So let's just first import the BERT tokenizer. So transformers, it's a simple statement from transformers import BERT tokenizer. And actually you can I have made this report on weights and biases. You can refer that, which also explains all of the code. This also, I don't know why this hasn't loaded properly. Let me just, okay, so let's switch to the report because that has more detailed explanation. On this Colab, I have kept the explanation to bare minimum because it's meant for execution. But here I've explained the code in more detail. So first of all, as we have already seen what tokenization is, let me just quickly walk you through what are the requirements that we need to satisfy to feed an input into the BERT model. So First of all, we need to add special tokens at start and end of each sentence. At the end of each sentence, we need to append a special separator token, which is represented by SEP, which denotes the end of a sentence. For classification tasks, we must prepend a special CLS token, which I have already mentioned in the beginning. The pad and truncate all sentences to a constant length. So let's just say the maximum length that we are going to support is 64. So what happens is, if a sentence is more than that, we have to truncate into 2 parts. And if a sentence is less than that, let's just say 50, we'll add a bit of spaces, a constant token that represent that this is just this character has just been added to make the sentence to a constant length. It is not used for training purpose. Okay. And the last part is explicitly differentiate real tokens from padding tokens with the attention marks. And the attention mask is simply an array of zeros and ones indicating which tokens are paddings and which aren't. So basically it means is that we know that we have appended a few extra tokens to make the sentence of constant length, but the model does not know that. So how do we send this message that, okay, these of the last few words are not meant for training? So that's when the attention mask comes in. So when attention mask is 1 and zeros, the position of ones indicate which tokens are padding, and zeros indicate which tokens are not padding, or maybe vice versa. So the model knows that which words are crucial to classify the sentence. All right. So let's move to the code. You've seen a small demo here how to initialize the tokenizer. Let's just do all things here. So on the right, you can see all the steps that are being performed here. So the step number 1 is split the sentence into tokens. Step number 2 is add special classification and separator tokens. Map the tokens to their IDs, which is indexes. Pad or truncate all sentences to same length. Create the attention masks explicitly. Differentiate the real from padding tokens. Which basically means creating attention mask, right? So to do that, the first thing that we need is the maximum length that we are going to use. Okay, so first initialize a tokenizer, and we are going to use BERT base uncased. So this is the base BERT model, and it is uncased. So if it is uncased, we have to pass do lowercase to true, because it will convert everything to lowercase. Now we have to calculate the maximum length that we need. So we'll calculate the length of the longest sentence for that. So sentences is basically the data that we have loaded, I guess, in here. I don't know. Yeah, sentences. Okay, so to encode, we'll first, to calculate input IDs, what we'll do is we'll call tokenizer.encode and pass a sentence and add special tokens to true. What it will do is it will automatically add the special tokens. Now to calculate the max length, we'll perform the max operation on the length of this particular input ID and length and the max, which is here a global variable, right? So it will automatically calculate the maximum length. So what's happening here? Here's the pictorial representation. I had that picture in the report, but I don't know, it's not loading properly right now. So let's just see what is happening here. So let's just say the total length of a sentence was 1, 2, 3, 4, 5, 6, 7. So let's just say the length of the maximum length of sentence is 7, and you have this sentence that says I like to draw, and you add a separator which indicates the ending part, and the classifier which indicates the sentence has to be classified, but the length isn't up to 7, so you add 2 pads, which means these are just extra words. So now this is how an attention mask will look. It will basically be 1 for all the words that are useful, that have to be looked upon, and 0 that indicates padding, right? So here it is. Here we are calculating the maximum length, and maximum length is 47. So instead of 47, we'll use 62, because here's the thing that we always try to use everything in 2's power. So just to be sure, we'll use max length as 64. So let's see what this function is doing, what this code here is doing. So we have already calculated right here the maximum length is 47. So I have not added all the code here in the report, and I have kept the code to bare minimum. Okay, so the next thing that we're going to do is we'll use encode plus. So what encode plus does is, encode plus is similar to this encode function that we have used here, except it returns both the encoded IDs as well as the attention masks, and we also need attention masks. So let's just see the argument that it takes. So we are looping across all of the sentences in the sentences array. So in the sentences array, so encoded dictionary return. So encoded dictionary is set equal to encode plus function. It takes a sentence, add special tokens to true, max length is 64, we have already calculated that, and pad to max length is set to true, and return attention mask is set to true, and return tensor is pt, which is basically means PyTorch tensors, okay, because we're going to use PyTorch. Alright, so now input IDs will append encoded dictionary input ID. So it basically returns a dictionary where input ID basically means input ID and the attention mask means attention masks. So we'll append for each sentence into this list, and we'll concatenate them together, and finally we'll convert the labels into a torch tensor. So we have everything tokenized now. Alright, so finally we move on to splitting the dataset. So to split the dataset, we'll use torch tensor dataset. We'll pass in input IDs and attention masks as well as labels into torch dataset, which will combine them to form a dataset. And finally we'll split the data into 90 and 10% for training and validation. So we'll calculate train size and validation size, and we'll use random split to split the data. Now finally loading the dataset. The next step is, so before we do that, here comes the part where we are going to experiment with stuff. So everything from here can be treated as hyperparameters. So as we have seen right here, that we have got 3 hyperparameters, that is batch size, epochs, as well as learning rate. So we cannot use a constant batch size for all of our all of our experiments. So here is the time where I will introduce weights and biases. So what weights and biases does is it automatically logs in your experiment it can log in any real value as well as an image. Maybe if you want to store if you want to log the output of a model or an image or something. So it can also visualize stuff. But another feature, that is hyperparameter sweep, lets you define a dictionary or a file. So here it is how I have defined it here. So it lets you define a dictionary that consists of a metric that is the name of the metric that you want to maximize or minimize. In this case, metric will have name of validation accuracy, and goal is to maximize that. Method is random. So basically, which means is it will run this code multiple times, and it will randomly choose a combination of these 3 hyperparameters. So the authors of this BERT paper suggested that these should be the hyperparameters for fine-tuning the model. So we don't know which is the best one or what is the best combination of all of them. So what we can do is we can easily automate the process of knowing and which one is the best combination by automating the process of visualization using weights and biases. So you just need this dictionary, right? So I have made this dictionary here, and next thing that you need to do is, you don't always need that sweep defaults, but I always try to have a default dictionary which is the default values of these hyperparameters. Not go over that right now, so let me just get rid of this. So what you do is, to create a sweep, you call this function won'tbe.sweep and pass in this dictionary, and it will generate a sweep ID. So what happens is every time the sweep runs, there is a dictionary called won'tbe.config that contains something like this. So it will have a separate value for all of these parameters, and it will have one of these values at random, right? So in that way you can use that dictionary to initialize your experiments, and then at each run that dictionary will get updated. So let's see it in action. How do we use that? So let's just say you have initialized a sweep. Now once the sweep is running, the batch size should not be manually set. It can be set by using by using won'tbe.config. Let me just see. Yeah, won'tbe.config.batch size, and I have just printed the batch size here. So it will just use the same old data loader from PyTorch, and it will use random sampler for training data set, and for validation it will use a sequential sampler because we don't need to shuffle the validation set, and it will basically return both of them. So here I'm using function because we need to call these, we need to reinitialize this data loader every time a new batch size comes into the configuration file. It means every time a new agent runs, every time this configuration gets updated, right? Okay, let's move on. Now let's set up a model for training. Again, we'll use a function here because we'll use a function here that returns the model. Okay, so we'll use a pre-trained model. So it comes from BERT for sequential classification dot from pre-trained. This function basically extracts or downloads the pre-trained model. We'll pass the name of the model, that is BERT pace uncased. Number of labels, so we are using binary classification, so it will be 2. And output attention is set to false because we don't need attention, and output hidden states is false, we don't need that too. Okay, and we'll return that. Alright, now finally we'll return an optimizer. To build an optimizer, we're going to use an implementation of Adam with weight decay that is found in HuggingFace. So that needs models parameters, so it will require a model as the argument. Again, we'll pass models arguments, and the learning rate will be won'tbe.config.learning rate. As you can see here, the dictionary will contain a learning rate because we are going to choose from these 3. Okay, and epsilon will be set to 1e-8, and we'll return the optimizer. Alright, now finally we'll have a learning rate scheduler, so we will return a scheduler, and that needs both optimizer and train data loader. Now this needs epochs. The number of epochs again is a hyperparameter that we have chosen, so it will be either 2, 3 or 4 that can be extracted using weights and bias config.epochs. Right, now basically we'll get a linear schedule with warm-up. So we'll pass an optimizer, number of warm-up steps is 0, and num training steps is total steps of train length of the train loader and times the epochs, and it will return a scheduler which basically will perform the weight decay. Alright, so here it is again setting up the hyperparameter sweep. It has to be executed beforehand, but yeah, here it is. So there's only one thing left to train our model. We'll create a configuration file that will list the values of hyperparameters that each hyperparameter can take. We'll then initialize our weights and bias sweep agent to log, compare, and visualize the performance of each combination. The metric that we are going to maximize is validation accuracy, which will log in training loop. In the BERT paper, the author described the best set of hyperparameter for transfer learning, and we are using the same set of hyperparameters. So these are the things, right? Now we'll create a sweep ID. Now finally the elephant in the room is this training function, the train function. So here we'll call this won'tbe.init. So this function has to be called every time you want to log something. So it needs to be, the won'tbe function needs to be, a won'tbe object needs to be initialized. So every time a new agent runs, we will initialize a new run. So this basically means that we want to initialize a new run. Again, we will same old PyTorch code, which is we have set the device to CUDA if it is available. Then we will call our function retModel to return the model. Then we will set that to device. We will load the data in optimizer, scheduler, all of that. Now finally, we will load the number of epochs from won'tbe.epoch, and we will run the epoch, right? So the first step is to enumerate the train loader. So the train loader, the data, as we have made our own data format. So the data comes in, as 3 parts. So the data consists of 3 parts. So the first part is the input ID, second part is input mask, and the third part is label. So we need to send all of these separately to the device model.0grad. Now finally we pass in the input to the model to get the loss as well as the logits. So this is all a HuggingFace model. So it automatically returns the loss and the logits. Logits is basically the predictions. So we need input IDs. Now token ID type is none. Attention mask is the input mask, and label is set to be label so that we can calculate the loss. So here's the syntax for logging anything. So use this write won'tbe.log and a list and a dictionary with the name as well as its value. So the name of the metric that we're trying to log is the train batch loss, because this is a train loss of a particular batch, and this is loss.item. And the total loss will be, we'll just add this loss, and then we'll basically perform backwards, and then we'll clip the gradient norm because we don't want exploding gradients, then scheduler.step and optimizer.step. We'll also calculate the average loss and training time, so we'll also log average training loss. Okay, that is it. Now for the same things are going to repeat for the evaluation loss, and just that we'll also log the evaluation loss, validation accuracy and average validation loss, all of these things. All right, now let's see what happens. Once you execute this code, the final step is to execute the sweep that automates the process of calling these functions multiple times over a range of combination of various hyperparameters. So how does that happen? You just run this function won't_be.agent and everything just takes care of itself. Now you can try this process by yourself. The link to this open source collab is available, but before that, let me just walk you through the outputs. So once you run this code, you get a link to this run page. Now this is the run page, right? This is BERT fine-tuning. So these are the things that we have logged. First is average training loss, validation accuracy, and training batch loss, right? So now, if you go to sweeps, this is one of the things that we have run. This is a sweep, and I think this one was once you go to the sweeps page, it gives you information about a lot of things. The first is the validation accuracy of each run, how they compare with the time they are created. So you can track how your models perform. The parameter importance with respect to validation accuracy. So we can see the number of the most important factor that affected the validation accuracy was epochs. So this is an information that this visualization provides. Another thing is the second most important thing was learning rate. And the third was batch size. This is how these parameters compare with respect to validation accuracy. 32 batch size with epoch 2 and learning rate of 5e minus 5. It gives a validation accuracy of around 83.4%. All of these things. So this is a really insightful visualization which tells you how all of these model performs, and this has been done automatically for you, and it is on the cloud, so you can just view it anytime. You don't have to have a system ready. These are things that we logged manually, so you can also compare the models like this, right? So this is an amazing tool. I suggest that you use it if you try to experiment with various data sets. So I hope you enjoyed this one, and I think that you should also go and check out the HuggingFace library for more details about how to get started if you found any difficulty following along with all the HuggingFace stuff, because it's really intuitive and the documentation is really great. And again, the link for this report is in description. Go check it out. So that's it for this one. In the upcoming videos, we'll cover a lot of deep NLP stuff. I wanted to cover all of these things a few weeks ago, but there have been complications and my work has been delayed, but I think I will start to cover stuff pretty soon. Have a great day.